right, welcome to the first Stats Lunch and Learn. We're going to be starting today with just talking about power, how you can use it in your research design, how it's going to help make studies better, and how improper uses of power can actually really hurt an otherwise good study. So when we think about what power is, there's a few things we have to consider first, and that's a type 1 and a type 2 error. As just a reminder, a type 1 error is simply the rejection of a true null hypothesis or just a false positive. So you found something, but there's actually nothing there. On the other hand, type 2 error, which is often forgotten about, is the non-rejection of a false null hypothesis, so a false negative. We think that there's nothing there, but in fact there is something there. And typically that has to do with poor study design, or as we'll see in a few minutes, power. And so like I said, this is incredibly important for this discussion for power, because power ultimately entirely influences your type 2 error rate. So a really good example of power, and an easy way to think about this, there's an example that hopefully will make power a little bit easier to understand. So at our REO staff meetings, 6 of us regularly tell bad jokes. So I just did a tally of the bad jokes from our last meeting. And as you can see, they were all over the board. Luke coming in hot with 30 bad jokes. I was behind him with 15, all the way down to Lori with 2 bad jokes. So using this example, we can make some predictions and try to test future bad jokes from this. So for instance, if we wanted to ask who's more likely to tell more bad jokes in the next staff meeting, will it be Luke or will it be Lori? That's a testable hypothesis, and we can use prior information to determine a likelihood for that event happening. So if we want to formally make a hypothesis for this, we can make our H1 that Luke is probably going to tell more bad jokes than Lori will. On the other hand, we also have to consider our null hypothesis that Luke's jokes are going to be equal to Lori's jokes. Using past information and using the prior information that we already know that Luke tells 30 bad jokes per meeting, Lori tells 2 bad jokes per meeting on average, we can use that to determine the likelihood of the H1 or the H0 occurring at the next meeting when we actually test it. So just using that information of Luke telling more bad jokes in the last meeting, we know that most likely Luke is going to tell more bad jokes at the next meeting as well. If we wanted to do a percentage on it, we could say we're probably 90% confident that Luke is going to tell more bad jokes, or 80% confident that Luke will tell bad jokes, with some wiggle room in there for error. So when we think about what that means, that's just simple probabilities that using that past information, the probability of Luke telling the more bad jokes is higher than the probability of Lori telling the bad jokes, or more importantly, the probability that they tell the same number of bad jokes, which would be that null hypothesis. And this is exactly what you can think of when you think about power. Simply the probability of rejecting the null hypothesis in those situations when the null is false. And so in this case, just like with the last example, directionality doesn't matter as much. However, power is just that ability or that likelihood or percentage to be able to reject a null hypothesis if the null is in fact false. And so to do this, we have to take, just like in the last example of taking the prior meetings to determine the likelihood of bad jokes, we can take all of the information that we have to weight those probabilities in favor of our hypothesis. And the benefits of this, a well-powered study is going to save time, it's going to save money, it's going to save participant costs. It's also going to, more importantly, avoid disseminating false information, because lower-powered studies are part of the reason of the replication crisis that is affecting so many fields right now. You can almost 100% weight that in the form of power, because it's underpowered studies that are finding things that aren't actually real. So when we think about this sort of a decision tree for power, we can look at 4 possible outcomes that depends on whether the null is true, the null is false, and whether we retain the null or reject the null. So we can see if the null hypothesis is actually true, there's no difference, and we retain that null, we've done correct retention. We have successfully retained the null. There's no difference there's no relationship. Our hypothesis was ultimately wrong. On the other hand, if the null is true and we reject that null, that's not going to be an issue of power. That's going to be an issue of our significance level. We probably have too liberal of a significance level, and that's a different issue in and of itself. We can't do too much about that with power. The other side of the table, though, if the null hypothesis is false, if there is in fact a difference between your two groups, if there is in fact a relationship between your two variables, and we retain that null, that's going to be incorrect retention and partly due to a type 2 error rate. On the other hand, though, if the null hypothesis is false and we reject that null, that's a correct rejection, and the entire likelihood behind that is power. So the entire right-hand side of that table with rejecting or with the null actually being false completely comes down to our power likelihood in our studies and how well powered it is. So if we think about it, if the null is true, if there is no difference, power is not even remotely an issue. So there is no difference between population means or the population core coefficient is 0. We just have a bad idea then. It doesn't matter how many participants we include in the study. If there is no difference, if there's no relationship, we're not going to find it with more participants. The other hand, when the null is false, that's when power especially comes into play. So there is a difference in the population mean, so the population correlation coefficient is different from 0. So with this, you want your project to be able to detect that falseness. You want it to be able to know how incorrect the null was or how false the null is so you can successfully reject it correctly. And so when we think about all of the things that are going to affect power, there's several things that we can do as researchers to modify our power. Now, whether we should do them or not is another story. And I'm going to go over those options that we have in our toolkit to affect our power. When considering that, though, one of the most important things to think about is the actual effect size. So how big is the difference? How strong is the correlation? How strong is the predictability? You may see effect sizes as Cohen's d. You may see effect sizes as eta squared, partial eta squared. You may see effect sizes as r squared, pure beta. There's Cohen's g. There's so many different effect size estimates out there, all of which are going to do the exact same thing. And I actually have a link later that you can use to convert your effect sizes and get your own effect size should you need it, or should you need to convert it to make it easier. So when thinking about what an effect size is, so just when comparing means, how big is the difference between the population means? Is it a large difference? Is it a small difference? A larger difference is going to be a larger effect size. A smaller difference is going to be a smaller effect size. Correlational results, how strong is the correlation? A correlation closer to 1 or -1 is going to be a strong correlation, whereas a correlation closer to 0 is going to be a weaker correlation, thus a lower effect size. And so with this idea, the bigger the effect size, the easier it is to actually detect a difference in the sample data. So if we want to think about this, a couple analogies. So if we want to think about this almost like a telescope, if you're looking for a really big star, you don't need a big telescope or a powerful telescope to find it. On the other hand, if you're looking for a little star that's way out there, you need a really strong telescope to be able to find that star. One of the other very easy things that we can do to affect our power, and this is the one that's most highly recommended, is to change our sample size. With a higher sample size, you have considerably more power. The larger the sample, the greater the power. And the reason for that, you're able to suck up a little bit of that error variance, and also you're able to just account for more of the difference. If you want to go into the math of it, it makes the denominator a little bit smaller, making it more likely for you to get a larger F or a larger T. So by upping your sample size, you greatly increase your power. So going back to that telescope analogy, you're looking for a star. If you have multiple telescopes and multiple people looking for the same star, you're going to be more likely to find it just because you have the more people. Similarly, if you want to increase power, use the right test. There's a lot of options out there statistically for testing, whether you want to jump into Bayesian structural equation modeling, whether you want to jump into true parametric, non-parametric tests. There's so many options that will ultimately get at the same result. However, depending on what test you use can absolutely affect your power. And so you absolutely want to choose the right test for the job. So the example I have up here is if you just comparing two groups. You could do that with dummy coding and moderated, or you could do that with dummy coding and regression. You could do that with a t-test. Technically, you could do it with an analysis of variance. You could do it with a Mann-Whitney U-test. You could do it with a Kruskal-Wallis test. You could do it with a Bayesian test. There's so many different ways to just compare two groups. In this example, though, if you wanted to compare a t-test and a Mann-Whitney U, for instance, the t-test is the more powerful test. It's a parametric test, and parametric tests are considerably more powerful than non-parametric tests. The issue is, though, obviously there are some violations that make the t-test weaker if you violate assumptions. But if you just have two groups that meet all of the assumptions of a t-test, run your t-test because it is the most powerful test compared to the Mann-Whitney U. Oh, and a good example, going back to the telescope example, an example of this would be using a telescope as opposed to using a cardboard tube with some glass on it. Use the right job to find the star. This one's especially controversial, and I highly recommend not doing it, but this does in fact affect your power. Change your significance level. Conventionally, we keep our significance level at 0.05. If you lower that, if you put it to 0.1, you're going to have more power. You're going to be more likely to reject the null hypothesis. However, that has a lot of issues because then you're going to get into the likelihood of increasing your type 1 error rate. So you can change your significance level, but I really don't recommend doing it. This would be similar to ultimately allowing you to decide or say on your telescope, saying, or lowering your threshold for what a star is. So for instance, any little speck that you see is a star, which that could easily be wrong. It could be dust, it could be a comet going by, it could be something on the lens. By lowering your significance level, you're increasing the likelihood of doing something wrong, of getting a false result. One of the next ones, and I do highly recommend this whenever possible and whenever able to do ethically, get rid of your variability. Cut some of that variability down or cut some of your individual differences down. Analysis of covariance was developed for a really good reason, and that was to get rid of covariance and to get rid of some of that variability and error. If you can cut down on your error ratio, you're cutting down on that denominator in the math of getting your F or your T, and that's going to make it more likely to find something. So in this case, recall that for two populations, the effect size of the difference in population means divided by the population standard deviation, and you can see the math there. Proper conduct experiment may affect the value of your standard deviation. The smaller the value, the larger the power. So simply cut down on that error, whether that's including some sort of covariate or whether that's collecting a more homogeneous sample, although there's some issues with that. I do highly recommend covariates. And the bright side about this, manipulating your standard deviation doesn't affect your type 1 error rate. It keeps it the same. So using that same telescope example for this, we could think of this as cleaning your lens, getting all of the little specks of dirt and dust off of the lens of your telescope so that you don't have, so you're not led astray by all the little specks when you're looking for your star. And one of the last things that you can do is use a directional hypothesis. So using one-tailed tests are considerably more powerful than two-tailed tests, so long as you specify the direction correctly. If you have really good prior theory suggesting that this group should be higher than this other group, or that this relationship should be positive, so long as you have a good theoretical framework for that, you can specify a one-tailed test and a one-tailed alternative hypothesis, and that's going to increase your power. You're not looking on both sides of the distribution anymore. You're only looking on one side of the distribution, which greatly increases your power. However, this is a gamble, because if you have guessed wrong, if there's some sort of boundary condition that's causing this specific group to flip from past research or this correlation to be different, there may actually be something there, but you've missed it because you've just looked at the wrong side. In this case, with the telescope example, knowing where to point your telescope to find the star. If you know the general area of space that it's in, you're more likely to find the star that you're looking for than if you're just kind of looking around blindly. So I have all of these examples here with detecting a difference and detecting a star. because for me, I find that as an incredibly easy way to remember ways to increase power. Larger effect sizes are easier to see. Larger samples give you more power. Choosing the appropriate test is absolutely something that you can do to increase your power. Don't recommend changing your significance level. That's highly controversial. I guess with some instances, some authors have recommended the p-value should always be at 0.01. So if you're sticking to 0.01, maybe then you could change it back to the conventional 0.05. But anything past that, I would not recommend it. Although there is also some discussion on what's known as marginal significance, which is that 0.06 to 0.1 range. Typically, I've always looked at that as, hey, we should look at this a little more, but we shouldn't probably make conclusions from it. So I recommend leaving your significance level where it's at. That's not a good way to affect power, but it will affect it. Cutting away some of that variability, including some covariates, finding some individual differences will certainly help to increase your power. And then one-tailed hypothesis testing, although you have to have good prior theory to successfully do the one-tailed hypothesis testing. So if we think of the way all of these work, there's really no downside to doing these. Technically, you cannot increase your effect size, but if the effect size is larger, again, that increases power. So if you look at if the null hypothesis is true, let's say there is no difference in the actual groups, or there's no relationship. Doing all of these things that increase power, with the exception of the significance level, it doesn't do anything. It doesn't make anything bad. It only makes your study better. On the other hand, if the null hypothesis is false, which we would expect, I don't know of too many instances where we would start a study thinking we're not going to find anything. Most researchers start a study because they think they're going to find something. If the null hypothesis is false, every single one of these options increase your power. And so there's really no reason not to increase power as much as possible, mainly because it's cheaper. You're going to use more participants, but in the long run, you're going to use less participants. And on top of that, it's going to be more likely to disseminate correct information to the scientific community. So when you're designing your studies, think about this table and think about ways that you can increase your power, and especially if you need to increase your power. So with all of that said, I assume many of you are asking, okay, how do we actually determine our power? How is that something that we're going to figure out? So the first place you want to start is you need to determine how big the population effect size you're looking for is. And so ultimately, this kind of leads to a catch-22. How do we know how big the difference is going to be before we run the study? Because we've not run it yet. So we shouldn't actually know how big the difference in the groups or how strong the correlation is. But I've just been telling you that you need to know how big the difference is before you run your study so that you can calculate your power. So Cohen, who's kind of the godfather of all things power, statistics, all things effect size. And you can even see more Cohen, Aiken, and West in there, who are huge names in stats. These are the three recommendations that they give to determine your sample size, working from number one down. Number one, to the extent that studies have been carried out by the current investigator or others are closely similar to the present investigation, the effect sizes found in these studies reflect the magnitude that could be expected. Look to other studies, in other words, that are similar. Look to those that have measured a similar outcome. Look to those who have used a similar manipulation. Your effect size is probably not going to be the exact same as theirs, but that's a good starting point. You at least have a direction to start from. Next, in some research areas, an investigator may posit some minimum population effect that would have either practical or theoretical significance. So with effect sizes, you can get to some really small differences. Some of the really small significance that I've seen have been 0.01% of a difference, and it's still come out significant. And you can get lower than that with enough power. So this suggestion is, how small of a difference matters? Does the difference, for instance, if giving one surgery technique increases someone's lifespan by 8 seconds, yet the surgery technique costs $10,000, is that 8 seconds worth the $10,000? So you have to consider those things. What is the minimum practical or practical theoretical significance of your effect that you would need. And you can set your minimum sample size from that. A third strategy you can do is to deciding what effect size values to use in determining the power of a study is to use certain suggested conventional definitions of small, medium, and large effects. This option should be looked upon as the default option only if the earlier noted strategies are not feasible. And this is one of the current issues we're facing with power, because a lot of people do this as the default. Just saying, oh, I'm just going to look for a medium effect just because I want to find a medium effect. Cohen outlines in the power primer what a small, medium, and large effect are. So a Cohen's D, a small one would be 0.3, a medium 0.5, a large one 0.7. Similar for correlations, it's going to be 0.3, 0.5, 0.7. R squared, you're going to look at 0.1 or 0.01 for small, 0.05 to 0.06 for medium, and then 0.11 to 0.12 for large. The exact same goes for eta squared, and it's slightly larger for partial eta squared. I don't remember those right off the top of my head. I think partial eta squared, a small is 0.03, a medium is 0.08, and then a large is 0.15, something like that. But there's so many publications out there that have these cutoff values that you can use. But once again, this recommendation is if you cannot do number 1 or number 2. In our line of work, 1 and 2 is the most beneficial option that we have for determining power. Use prior studies that are similar, especially if you can get multiple prior studies, and then determine what actually matters. How much of a difference is actually needed for this research to be important or practical? So when actually determining the desired power, we have to think about how much power do we want? Because too much power can sometimes be a bad thing, and we'll talk about that near the end. But how much power is just enough? And so with the desired power, it's the probability of detecting the difference we think our manipulation will make. So we can think of this probability on a 0 to 1 scale. And on average, this value is set at 0.8. We want 80% power in determining the likelihood of finding something. I've hunted everywhere. I've had professors that I've worked with hunt everywhere. We have no idea where that 0.8 suggestion came from. It's almost like the 0.05 for a p-value. It's somewhat arbitrary, but it seems to have caught on, and now everyone's using it. And if you do something different, you're probably not going to get published. Power is a little bit more flexible than trying to change your p-value, but I recommend setting your power to 0.8. 80% likelihood of finding an effect should an effect actually exist. That keeps your type 1 error rate low, that keeps your type 2 error rate low, but also keeps you from getting stuck in the weeds of dealing with something that's predicting less than 1% of the variance. So one of the first ways that you can actually do this to determine your sample size, how many participants you need, is you can consult a sample size table or a computer program. I have a link here to one of my former instructors at University of Tennessee at Chattanooga of a bunch of power tables. Basically, they're tables, and they will show you, okay, let's say I want this effect size with this much power, and it'll take you over to a number, and that's how many participants you need. I will let you all go through those sort of in your own time if you want to, because just for the sake of time. But these power tables are really useful because they're a very fast and convenient way of finding something. And so, for instance, I choose a sample large enough to have an 80% chance of detecting a medium effect. So go to the column that says medium effect, go to the 80% and see what number it spits out. Or if you want to have a sample large enough to have a 90% chance of detecting a population R of 0.11, go to where so R is going to be a small correlation, go to a small correlation on the table, go to 90% power and see what number they both show you. And that's going to be how many participants you actually need. More importantly, though, and thanks to modern computers and computing, we have actual power analyses. So it's a statistical method. I'm going to talk about how it's actually done, and then we're going to end by actually doing a few. That's why I recommended downloading GPower on your personal computers, because it's not approved at Cook yet, although we're hoping it will be approved very soon. The request has been put in. The power analysis simply returns the probability of attaining a true finding if the null is false. And so you can do this a lot of ways. You can do it in GPower, which we're going to talk about. Sample power is SPSS and IBM's answer to GPower. It's got benefits, but honestly, it's very limited compared to GPower. The power package in R is amazing. I cannot stress enough how awesome it is. However, you have to know how to code and use R, which has a learning curve. And then you can also just use SPSS, but I cannot stress enough, you're going to be doing it for hours. One power analysis for hours in SPSS if you try to do it. It takes forever, and ultimately you could do it by hand faster. So once again, we're going to be focusing on GPower in just a moment. But here's another example, and we're going to be computing power, and I'm going to show you sort of the math behind the scenes of what is happening to get this percentage number. This is one of those that you don't so much need to know how the car works to be able to drive a car, but I'm a firm believer in you should really know how to do stats if you're going to be using a processor to do stats. So I am going to show you how power would be conducted, or how it would be computed before we actually try to compute it. So in a previous study, a study was conducted comparing test scores between two groups. One group received a stereotype threat prior to the test, the other group did not. You don't have to know what stereotype threat is. This is just one study that used two different groups and measured an outcome. Their hypothesis was that the stereotype threat group would perform more poorly than the control group. So that means the alternative hypothesis being the stereotype group and the control group are going to be equal. So we can see the N of each group. So the stereotype threat group had 12 participants, the control group had 11. We can see their mean scores on that test, and we can see the standard deviation. With typical reporting practices on journals, you're also going to give a t-value and you're going to give a p-value. Fortunately, now they also give you an effect size. That's been one of the really good things that's come out of this replication crisis, is that more and more journals are requiring effect size estimates as part of their reporting practices. However, if you find a study such as this one that does not include the effect size, there are ways to calculate it just from this information. So let's start just by looking at the means and standard deviations of each of these groups. We can assume that if their data is true, if their results are true, that should we replicate this, we will find a very similar result. Our means and our standard deviation should look about the same if what they found was true and we try to replicate it. So if we want to try to replicate it, we need to find their effect size. And there are so many online calculators where all you have to do is punch in the mean, punch in the standard deviation, punch in the t-value, punch in the regression, punch in the R, punch in the t, whatever. I have one here that I reckon, this is typically what I use when I'm looking for an effect size. You can use that link and it'll take you straight to social statistics. And it just computes effect sizes for you. I also have an Excel document that will convert effect sizes among themselves. So it'll automatically convert a D to a G or to an eta squared or to an R squared. I'm happy to share that if you would want it. But like I said, there's so many online calculators that are really easy to use. All you have to do is really Google online effect size calculator, and this will probably be the first link that actually pops up, but you'll find so many of them. So if the actual math behind this, if we want to determine our power, we are going to take the t-value that we would get and the effect size value that we would get, and we are going to simulate 10,000 samples of these two populations with the same mean and the same standard deviation. And so the area that falls above that significance value, that is your power. The percentage of that is your power. So in this case, if we were looking for, using that same data, if we were looking for a t of 2.024, using those same means and standard deviations, our power would be 0.86, because that is what is above the curve for that t-value cutoff for significance, again, using that same mean and standard deviation. Power is simply the percentage of the normal curve above the cutoff for significance. And so this is the SPSS way. You have to simulate that data yourself using normal distribution, what is it? It's norm dist probability estimate function. And it takes quite a bit of time to use, quite a bit of time to do, and it's also very frustrating to try to do. So I never recommend doing this, but this is how it works. It's generating this normal curve with sample data based on your average difference and your average standard deviation between the two groups for a two-sample test anyway. Or we can save a whole lot of time and just use GPower. Here is the link to GPower if you don't already have it and haven't already seen it. Pretty easy to use. The actual user instructions are very in-depth and very handy. They go into great detail on every single test that you can do. And so the nice thing about this, we can use GPower for literally anything. So I have GPower up. Let me pull it over, maybe. There we go. Can you all see GPower, or do I need to change what screen I'm showing? Okay, I'm seeing some head nods, so I will change the screen. There we go. How's that? Perfect. So this is what GPower looks like when you bring it up. So what we were just doing, we were doing a t-test, a two-sample t-test. So the first thing you're going to look for is your test family. So you've got exact tests, such as Fisher, such as chi-square, f-tests, such as analysis of variance. Regression also sometimes falls in this one, in MANOVA, as well as analysis of covariance. T-test is going to be more correlation. It's going to be some linear regression. It's going to be actual t-test. We know what chi-square test. And then I don't know too many people that actually use z-test because we don't typically work with populations, but those options are there. So for a two-sample t-test, we're just going to start by clicking t-test. Then we're going to find the test that fits what we need. So t-tests are mean differences, so we can automatically move down here. We don't want to work with a Wilcoxon signed rank or a Mann-Whitney U, so we can skip those. So here we're looking at difference from constant, so this will be a one-sample t-test. Difference between two dependent means, so this would be a dependent t-test, not what we're looking for. On the other hand, difference between two independent means or two groups, that would be the test we would be looking for an independent samples t-test. For types of power analysis, typically we're going to focus on a priori, although sensitivity is an incredibly powerful tool that if we have time, we'll talk about. An a priori test, this is your power analysis. Generate what power you have prior to completing the study. GPower defaults to a one-tail. Typically, we do two-tail tests, although, as I said earlier, a one-tail test is going to be more powerful. So I'm changing that to two-tail. You never want to change your alpha, your error probability. This is your type 1 error rate. This is your p-value. Keep it at 0.05. This 0.95 is your power, so I'm changing it to 0.8 just because that's the typical suggestion that you end up keeping. This effect size, so if you hover over it, it'll give you estimates of effect size. So D 0.2 is small, 0.5 medium, 0.8 large, with some suggesting 0.7 will be large, but still. So in this case, if we were looking for a medium difference with an error probability of 0.5 and an effect size or a power of 0.8, we can just run the test. This allocation ratio, this is going to somewhat be the difference, not so much the difference is effect size, but the allocation of like size between N2 and N1. Is group 1 going to be larger than group 2 as far as the number of participants? So in this case, you want them to be the same. You want them to have the same or a similar number of participants. So you're going to keep that the same. So once you click calculate, it gives you that same error curve or that same normal curve that I was talking about earlier. And so it's going to show over here that if you have a sample size of 128 participants, that's 64 per group, your actual power is just over 80%. So an example with this allocation ratio, though, let's say we changed this to 2. Notice that group 2 is now twice the size of group 1. So all of this allocation ratio is how many participants are in each group. But typically, a priori, you want to keep that to 1. So let's increase our power. Let's say we wanted 90% power. In this case, to get 90% power, we're going to need more participants. More participants increases your power. And so with 172 participants, 86 per group, we're going to have 90% power. If we further down to 0.7, we'd only need 102 participants, 51 per group. However, once again, you probably want to keep that at 0.8 or above. There's nothing stopping you from going above to get more power. I am an avid advocate of more power to studies because it just makes the study better. But feel free to go above. I so recommend not going below 0.8 though. So this is how to do a t-test. There's so many other types of tests we can do. So if we wanted to look at a correlation, so the point by serial model, two-tail test, effect size, once again, it's going to give you estimates of what the size of the effect is. Here's your alpha probability, and here's your power. So I'm going to set that to 0.8. I'm going to calculate. So for a medium size correlation with 80% power in a two-tail test, we need 82 participants to find that. As you can see, if we dropped it down to one-tail tests are more powerful, so we don't need as many participants. But once again, we're less likely to do one-tail tests. And from my experience, so as a reviewer, anytime I've reviewed a paper that's done a one-tail test, I've been very skeptical of it. It automatically raises red flags for me and makes me think, what are they trying to hide? Why did they not do a two-tail? Does the result actually work out if the two-tail test works? And just from looking at the literature, one-tail tests are way less respected and accepted than two-tail. Saying that, one-tail tests are still published, and there are absolutely reasons to use them. Just make sure your theoretical reason for using the one-tail test is valid. So we can do more. We can do regression. So we can do simple linear bivariate regression. In this case, this is going to be more closer to dummy coding. So two groups difference between intercepts and slope. So that's going to be straight onto dummy coding or moderation. One group, size of slope, this is going to be a simple linear regression. Under F-tests, we can also find linear multiple regression. This is what I recommend doing for regression because it gives your actual model and your R-square, your likelihood of increasing R-squared based on models, and your R-squared deviation from 0. Under your chi-square test, again, generic chi-square, goodness of fit, which is often what we're doing. Not too much variance testing with chi-square from my experience and from what I'm seeing that we tend to be doing around the department, but the generic and the goodness of fit tend to be the most common here. There are a lot of other tests that we can do, however. So I'm going to switch back to the PowerPoint because we're going to talk about a few of those. Oh, I'm actually just going to pull up screen one because now you should be able to see everything. Okay. So with analysis of variance, it's going to be very similar to t-test, except it's going to take more predictors into account. And this is literally what GPower was designed to do. GPower was designed for analysis of variance. And honestly, if you look at the GPower manual, it's got the most support to it. And so analysis of variance is really easy to do under the F table. So if we wanted to find it, F-test, analysis of variance, so fixed effects omnibus, this would be a one-way analysis of variance. If we move to fixed effects, special main effects, interactions, this would be a two-way analysis of variance or an interaction design with mixed model. We have between factors, within between interactions with a mixed model analysis of variance. All of these, it just depends on what research you're looking for. So in this case, if we had a one-way analysis of variance, medium effect size, I'm going to move this to 0.8. And the number of groups we had, let's say we had 4 groups. In this case, to find that medium effect, we'd need 180 participants. So that would be 45 participants per group to have a minimum power of 0.8. Keep in mind, I say all of this, however, all the power in the world won't fix a bad idea or a bad study. So just because you've met your power assumptions doesn't mean you're going to find significant results all the time. Power is a good way to make sure the study is better, but it doesn't fix everything. If your idea is wrong, your idea is wrong, and no amount of power will fix that. And that happens. If I had a nickel for every bad study idea I had that was properly powered, I would not need to work a job because I would have that much money just from bad ideas. So power is a good tool, but don't think this is going to fix everything. If we wanted to go with regression, there are some issues here, unfortunately. GPower does not handle regression well, mainly because you can keep adding predictors and it does not appropriately increase your sample size need. So there are some other rules of thumb that you can handle for a regression model, especially with multiple regression, moderated regression, and mediated regression or conditional process. Some recommend 10 to 20 participants per predictor. This is good in theory, but horrible in practice, in the sense if you only have one predictor, that's suggesting you only need 20 participants, which is going to be way underpowered. Howell has recommended 50 plus 20 times the number of predictors, which gets you at that minimum of 70, which is better. That's much better, but it's still often lower powered. And then Keith's going to recommend 200 plus minimum for a regression. It doesn't matter if it's simple linear, it doesn't matter if it's multiple regression. I tend to fall under Keith's recommendations of that 200 plus for regression. Regression is a very powerful tool, but it's incredibly easy to abuse and misuse. So the more power, if you're doing a regression, I would argue the better. And similarly, you can use this as a rough estimation of mediation. If you look back to the old school way of doing mediation of measuring your A path, measuring your C path, measuring your A path, and then measuring your B path plus your C prime path, you can do that with mediation by just lumping in both your mediator and your predictor together, and that would be a rough estimate of mediation. Moderation, there's no way to do that in in GPower unless you cheat. Moderation is now because of advances in our ability to understand the regression model. Every single analysis of covariance you do, every single analysis of variance, every single t-test you're doing is using regression. It's just whatever stats processor you're using is just hiding it. So SPSS, for instance, when you're running an analysis of variance, you're actually running a regression, and it's just hiding some of the regression stuff and making it look more ANOVA-y. So you can use this to your advantage in GPower, and you can trick GPower into doing a moderation analysis for you. You just have to treat it as an analysis of covariance, because the analysis of covariance in GPower handles interactions between your covariate and your independent variable, which is exactly what moderation is. So if you want to run a moderated design, you just need to run analysis of covariance. And again, I will always recommend moderation when possible, because that's going to eat away at some of that variability, and that's going to increase your power likelihood because there's going to be less variability. If you need an effect size converter, by the way, here's that spreadsheet that I was mentioning that will convert any effect size you need. Because sometimes, let's say you're wanting to run a t-test, and typically that's Cohen's D, sometimes G. And for some reason, the paper that you're reading to look for power decided to give you partial eta squared for some reason no one knows. You can use this to just put in what that partial eta squared is, and it will convert it straight to a G or to a D. This is also really useful if you're trying to do meta-analysis. So sort of wrapping up, why should we be concerned about power? So assuming that we create our treatments to make a difference, assuming that our studies are designed to make a difference, it only makes sense to conduct research that has the greatest probability of detecting a difference that we set out to make. Why would we even do the research if we didn't want to ultimately find something out, or to make that difference, or to understand a population or a group or a treatment better? Second, this can really provide insight into why we failed, why our study failed. If we're running a study that we really think should work and it doesn't, and all the theory is saying, yes, this should work, we can look to power and say, and to try to cross that off list, was power the reason it failed? Did we simply not have enough participants to find the difference that we hypothesized? On the other hand, though, there are reasons that we don't want high power. The first one being you're not interested in the difference and don't have time to explain why you found it. Some really large studies that have a lot of dependent variables and a lot of things that you can ultimately predict, sometimes you really don't care about the differences between some groups. And if you have really high power, you may find those differences and have to explain them. So a perfect example, a study I published a few years ago, I had just a manipulation check, or not a manipulation, excuse me, a delay between my manipulation and my dependent variable. I just needed to get their mind off of what they were doing and think about something else. Well, when I was running the analyses, I had a reviewer, when I tried to publish it, I had a reviewer ask, hey, did anything happen with the manipulation check? They were just curious. So I ran that, and sure enough, the manipulation check, there was a significant difference between my two groups. And I'm thinking in my head, oh no, I don't want to have to explain this. I don't even know where to begin to explain this difference. And the reason I found that difference, it was an incredibly small difference, but I had a lot of power. And so then I had to explain that difference that I didn't care about, that was peripheral to the paper. And the only reason I had to explain it was because I had too high of power for that. Another reason you don't want to have power, you're overwhelmed by the differences already and don't have time to deal with any others. Some larger data sets, if you're looking at correlations, for instance, you can just dump a ton of stuff in there. And there's so many things probably going to pan out. This can actually lead to some issues with p-hacking, can lead to some issues with phishing, especially, where you don't have good prior theoretical reasoning, but because you have so much power, you're finding significant differences when those differences don't actually matter, and you've not gone through the proper steps of hypothesizing these differences. And then lastly, the difference is incredibly small, and you don't care about it. So the example I gave earlier, if a treatment that costs $100,000 increases someone's lifespan by 8 seconds, that's probably too small of a too small of a difference to matter. $100,000 for 8 seconds is probably too small to be worth the research going into and to be worth actually the benefit of the project. So in a nutshell, that is power. We have some time. I will gladly open it up to questions. I also have my contact information on here. If you have any other questions at any time, feel free. Power is one of my favorite things in stats, so I will happily talk your head off about this all day.